Hello, I'm going to present you our work about combining coupled hydrological hydraulic modeling of river networks and sparse multi-satellite observations to define stage fault discharge laws. The purpose of the study is to compute discharge from satellite data. This discharge will be computed using SFD laws that links discharge, water surface elevation, and slope. However, one of the challenges is the slope estimation, especially with strong hysteresis behavior. Altimetric data sparsity implies that the slope estimation to be rather inaccurate. Moreover, only the surface is observed while the bathymetry and the bed friction is not. To derive such law and its a set of parameters, a calibrated hydrodynamics model is going to be used as extrapolator. This study is illustrated on the Rio Negro-Rio Branco network located just above a major confluence and hence affected by a backwater effect. The river flow model is the Saint-Venant equations. The multi-satellite data, such as the Peckel water mass, the altimetric data, and the MGB model are used to construct the effective model. Once the effective model calibrated, the slope and the discharge are extrapolated from the model output to complete the satellite data. And then the altimetric and extrapolated data are used to calibrate the set of parameters. The calibration of the model is about obtaining a waterline that goes through a noisy cloud of altimetric data in a physically meaningful way. In this study, calibration of the model is about inferring the Strickler coefficient at the virtual station, since we are interested in the behavior at this point. A good calibration provides a physically meaningful discharge and consistent with the water surface elevation observations on the whole time window and at any numerical nodes, and hence can be extrapolated. Hysteresis in varying backwater implies that the estimation of the slope and its scale may be important to estimate discharge. The large-scale slope is averaged over 10 km reaches inside the altimetric grid to be consistent with the scale and of the estimation of the future mission spot. The calibration of the SFD parameters implies that the discharge computed by the SFD law will be model-like discharge. The presented results are the results of a S3A station affected by the backwater effect, which explains the hysteresis. The slope analysis shows that the water surface curvature is locally the same size, and hence one can deduce slope averaging trends, which is the large scale slope is always greater on this station. Other stations with various location and hydraulic control has been studied. Several SFD laws have been computed with different set of parameters and with different slope estimation on this virtual station. The results are rather accurate with the fine and large scale slope, but less without slope. In the presented results, only the top width is used and the cross-section are supposed to be rectangular. Reasonable hypothesis in the Negro River basin. It is possible and likely to be useful when the cross-section may be less rectangular to consider varying width and add the power over the width in the set of parameters. The time extrapolation from a calibrated model is rather successful and the slope enables us to capture more complexity of the floor. It is possible to do space extrapolation. Here it is about computing SFD laws where the model wasn't calibrated. This extrapolation is possible when the water surface slope reflects the main hydraulic control.